Our subject is digital signal processing. Now we are going to discuss about fast Fourier transform. So that is DIF, Radix to FFT algorithm. So DIF is nothing but decimation in frequency Radix to fast Fourier transform. So before that we should know that the Fourier transform. So normally the Fourier transform is a image processing tool. So this transform is used in the image analysis and image reconstruction like this. So normally the Fourier transform converts the time domain sequence into the frequency domain sequence. So now the DIF Radix 2 is one of the fast Fourier transform. So before that we should know what is meant by fast Fourier transform. So in normal direct computation of DFT, so it will take more times to calculate the discrete Fourier transform. So here fast Fourier transform as compared to direct calculation of fast Fourier transform, the computation time is low. Next, from this session, the students can able to understand the concept of fast Fourier transform algorithm, and they can apply this algorithm to determine the transform of any sequence. So here the fast Fourier transform is a method for computing the discrete Fourier transform with reduced number of calculations. So with the help of fast Fourier transform, we can calculate the discrete Fourier transform with reduced number of calculations. That means the calculation time will be reduced. So the computational efficiency is achieved. Here this method follows divide and conquer approach. In this method, so this method decomposes an endpoint DFT into successively smaller DFTs. So here we can after that we are analyzing all the smaller DFTs to calculate the endpoint DFTs. So here this is the Radix to FFT. So in an endpoint sequence, so in Radix to FFT, the endpoint sequence can be represented by 2 power m. That means this is the Radix 2. So 2 power m. So here m is nothing but the number of computation. So for endpoint sequence we can write n equal to 2 power m. For like this, if it is a 8-point DFT means we have to write 2 power n, 8 equal to 2 power 3. So we have 3 stages of computation. So here m is nothing but the number of stages of computation. For 4-point DFT, 4 equal to 2 power 2. So here we need 2 stages of computation. So next, this is the formula for the Fourier transform. X of k equal to sigma n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n. So here in fast Fourier transform, they are introducing one twiddle factor. So with the help of twiddle factor, we can easily identify or we can easily simplify x of k. So in order to simplify this notation with the help of twiddle factor. So in this method, fast Fourier transform method, with the help of twiddle factor, we can simplify the discrete Fourier transform expression. So Wn is the twiddle factor equal to e power minus j 2 pi by n. So here we can write x of k equal to sigma n equal to 0 to n minus 1 x of n into w power nk into n. So instead of e power minus j 2 pi by n, we are writing wn. So here nk. So this is the twiddle factor. So here the calculation will be simplified with the help of twiddle factor. Next one, DIF f of t. So DIF, decimation in frequency Fourier transform, fast Fourier transform. So in this algorithm, the endpoint time domain sequence is converted into two numbers of n by 2 sequences. Then again this n by 2 sequence is converted into two numbers of n by 4 sequences. So this process is continued until we get n by 2 number of 2-point sequences. So this is the procedure for calculating discrete Fourier transform in DIF f of t. So here for n point DFT means we need m number of stages of computation. So n equal to 2 power m. So this is the basic flow graph for the DIF f of t algorithm. So here we have two numbers, complex numbers a and b. So here this is the basic flow graph. So in this point, so it receives a signal and b signal and add. So this is the comparator. So a plus b. So a equal to a plus b. So this is the complex numbers a and b, and after processing it will make another complex number capital A equal to a plus b. Here, so in this place it receives the signal a and this b is multiplied with minus 1. So for flow graph, the lower point of flow graph is multiplied with minus 1. So a minus b. After that, this subtraction is multiplied with twiddle factor wn power k. So we will get b equal to a minus b into wn power k. So this is the basic flow graph for DIF f of t algorithm. So here for example we are considering 8-point DFT DIF Radix to f of t. So 8 point. So we have to write n equal to 8. Next, this is the standard equation for the calculation of number of stages. So n equal to 2 power m. 2 is the radix. So this is the radix to f of t. So we are writing 2 power m. So now how will you write 8? 8 equal to 2 power 3. So we have 3 stages of computation. But in DIF Radix to f of t, first the endpoint DFT is divided, is decimated into 2n by 2 point DFT. That means here this is 8-point DFT. So this is the 8-point DFT can be divided into 2n by 2 point to 4-point DFT. So here 8 point. So it is divided into 2 4-point DFT. Because in DIF Radix to f of t, the endpoint DFT is divided into 2n by 2 point DFT. So like this, here this is 8-point DFT. So this 8-point DFT is divided into 2 4-point DFT. Again, each and every 4-point DFT. So this is the 4-point DFT is divided into 2 2-point DFT. So here's this 4-point DFT is divided into 2 2-point DFT. Again, this 4-point DFT also divided into 2 2-point DFT. But for DIF Radix 2 algorithm, we are writing the input sequence in a normal order. But in the output side, we are getting the output signal will be in bit reversed order. And here for this is the 8-point DFT. This is 8-point DFT. So 8-point DFT we have 4 twiddle factors. So for the DIF radix to FFT, after the calculation, that means here this is the addition and the subtraction. After the addition and subtraction, we are multiplying the twiddle factor. So here after this value, after this subtraction, we are multiplying the twiddle factors. So for 8-point DFT, we have 4 twiddle factors: W8 power 0, W8 power 1, W8 power 2, W8 power 3. And for the 4-point DFT, we have 2 twiddle factors: W8 power 0, W8 power 2. W8 power not 2, C1. And here for 2-point DFT, we have only W8 power 0, only 1 twiddle factors. Next we are going to see the calculation, stages of calculation in separately. So here flow graph for first stage of computation. So here we are writing the input x of n, that is the input sequence. So x of 0, x of 1, x of 2, x of 3, 4, 5, 6, 7. So we are writing the sequence in a normal order. Always in DFT, in 8-point DFT, the last 4 lines are multiplied with -1. So here we are getting, so this point it receives the signal x of 0, and here also it receives x of 4. So you will get x of 0 plus x of 4 equal to G1 of 0. We are giving new name G1 of 0. Again here also it receives x of 1 and x of 5. This x of 5. So 1 plus 5. Here also it receives x of 2 and x of 6. Here x of 3 and x of 7. And here, so in this point it receives the signal x of 0 minus x of, it receives x of 0 and x of 4 is multiplied with -1. So x of 0 minus x of 4. In this point we have x of 0 minus x of 4, because x of 4 is multiplied with -1. Then this value is multiplied with W8 power 0. So x of 0 minus x of 4 into W8 power 0. This is G2 of 0. Like this, the same process will be there. Here it takes x of 1 minus x of 5 into W8 power 1. So the same calculation will be there. So next we are going to, so these are the output of the first stage of computation. So this output is given to the second stage of computation. G1 of 0, G1 of 1, G1 of 2, G1 of 3. So like this. So these are the output of first stage that will be given to the input of the second stage. So here we have 2 4-point DFT. So here the bottom line we are multiplying -1. Here also we are multiplying -1. Next here this is the twiddle factor W4 power 0, W4 power 1. W4 power 0 and W4 power 1. So for 4-point DFT we have 2 twiddle factors. 4 point. So Wn value 4. So next here it receives G1 of 0 plus G1 of 2. And here also it receives G1 of 1 plus G1 of 3. Addition. So here it receives G1 of 0 minus G1 of 2. Why here we have minus? G1 of 2 multiplied with -1 and comes here G1 of 0 minus G1 of 2. This value again multiplied with W4 power 0. So that value will be D12 of 0. So like this we have here G1 of 1 minus G1 of 3. into that answer multiplied with W4 power 1. So G1 of 1 minus G1 of 3 into W4 power 1 equal to D12 of 1. So this is the same process will be continued for this 4-point DFT also. So these are the output of the second stage of computation. Next, this output is given to the third stage of computation. So in third stage we have 4 2-point DFTs, because in the previous stage 4-point DFT is divided into 2 2-point DFTs. So here we have the only one twiddle factors W2 power 0. So we have to introduce the W2 power 0 here. Next, in the bottom of flow graph we have minus 1. So here it calculates here D1 of 0 and D11 of 1. So we have D11 of 0 plus D11 of 1. Again here it receives D11 of 0 minus D11 of 1. Then this value is multiplied with W2 of 0. So that answer D11 of 1, that will be equal to X of 4. Because the output of the third stage should be in bit reversed order. So this process, so same procedure is continued for all the other 2-point DFTs. So we will get X of 0, X of 4, X of 2, X of 6, X of 1, X of 5, 3 and 7. So here in DAF FFT algorithm, the input we are giving the bits in normal order, but in the output side we are getting the bits in bits reversed order. Okay. So this is the procedure for calculation of DFTs by using DAF Radix to FFT algorithm. Thank you. So this is the combination of all stages. First 8-point DFT, again to 4 point, finally 4 2-point DFTs. Thank you.